So in order to describe a chemical reaction that's occurring, chemists like to use what is known as a chemical equation. So for example, if we were to describe what's happening when coal is burning, it turns out is that for every one atom of carbon, it reacts with oxygen, and in that reaction you create one molecule of CO2. So the ratio of the ingredients there is that there's for every one carbon and every one molecule of oxygen, you get the product, 1 of carbon dioxide. So the number in front of all those elements is what we call a coefficient. And when a coefficient is 1 in a chemical reaction, we usually omit it. So this reduced down to just simply carbon plus oxygen equals or arrow sign carbon dioxide. So, and now let's take a look at our next example of iron rusting, right? So if iron, if you let it sit out in the air for some time, it begins to react with the oxygen in the air, and that oxygen and iron reacting together will form a new product called iron oxide or iron 3 oxide that will just be on the outside surface of your iron, like the rusting nail. Right? So the chemical equation for that reaction turns out that for every 4 atoms of iron, you react with 3 molecules of oxygen to give you 2 units of Fe2O3. So an analogy to help you understand what a chemical equation is think about a recipe. So for example, if I wanted to make s'mores, the recipe for s'more would be that you need 2 crackers and 1 marshmallow and maybe 3 pieces of chocolates to give you 1 s'more. Right? So if I were to transform that into a chemical equation, you can say that it looks like this. Right? 2Cr plus 1M plus 3CH equals a s'more, or we represent s'more as its components as Cr2, M, CH3. Okay, so now that we understand the concept of the balanced chemical equation as a recipe, you can now answer questions like this. So if I want to make 20 units of iron oxide, how many molecular oxygen molecules would be needed? Okay, so the questions again state that you have 20 things of iron oxide. If I have 20 things, if I wanted to make 20 things of iron oxide, how many of the molecular oxygens do I need? Right? So we need basically, this recipe says that for every 2 that is made, you need 3 of the oxygens. So that's their equality. Let me write on the side here that equality is that for every 3 oxygens, whatever, I'll just call that unit of oxygen, there is going to be 2 of iron oxide. Remember, that's the recipe. Or the reverse, right? For 2 iron oxide for every 3 oxygens. In this case, if I want to convert iron oxide into oxygens, I'm just going to use that straight. 3 of oxygens for every 2 iron oxide. Notice that iron oxide goes away. Giving you how much oxygens you need, which is the unit oxygens there. So that's 20 times 3 to the power 2. That's going to be 30 oxygens. Okay, so simply answer that question is, if I had 30 molecules of oxygen, I would make 20 molecules or this compound of iron oxide. If you make 0.35 moles of iron oxide, how many moles of oxygen is that? So again, you say that 0.35 moles of iron oxide is going to give me how many moles of oxygen. So again, the ratio would be for every 2 moles of oxygen of iron oxide, you're going to get 3 moles of oxygen. Remember, we're using moles here, not just the individual count. Still, you will see that cancellation of moles of iron oxide. So let's do the math here. 0.35 times 3 divided by 2 is 0.525. Thinking about sig figs, again there's no sig figs here because this is an exact number. 3 to 2 are exact. So there's only 2 sig figs, so this becomes 0.53 moles of oxygen. Okay? So let's briefly talk about what are the components in a chemical reaction. In a chemical reaction, you write on the left-hand side the reactants, and on the right-hand side the products. And the reactants becoming a product is indicated with that arrow. If heat is a part of this reaction, sometimes you might see the delta sign either on the left-hand side where heat is added, or on the right-hand side, which means heat is the product. After you write the chemical compounds, you might also have to write the states they are in. And the states that we know are solid, liquid, and gas. And the fourth kind of state you might see is this thing called AQ, which stands for aqueous or aqueous, however you like to say it. It just means that there's a solid dissolved in a liquid, whatever that liquid would be. And that liquid actually is water, right? So whatever solid is often water, we call that aqueous. Right? Aqua means water, right? Okay. And lastly, in a chemical equation, you would need the coefficients, which are the numbers in front of the chemical compounds. Another thing that you need to be able to do is balance chemical equations. And the premise behind balancing chemical equations is the fact that no matter is created nor destroyed. They can only rearrange, right? So that's the whole premise of chemistry. Things cannot be created or destroyed, so that if you have an oxygen atom here on the left-hand side as a reactant, at the end you also have to have one oxygen atom as your product. It may be by itself in one case, but then it joins something else in another case, but it's still there, right? Okay, so let's take a look at how we were able to derive the balanced chemical equation that we saw earlier. So we got iron, let's say, reacted with oxygen, and that's creating a rust chemical compound called Fe2O3. Okay, so to balance chemical equation is just like balancing your, like doing accounting, right? So the simplest way is to keep exactly how many individual atoms you have at the beginning and at the end. So on the left-hand side is your reactant, and on the right-hand side is your product. Right? So how many ions you have beginning? 1. How many oxygens do you have at the beginning? Oxygen atoms? 2. Right? How about on the end? How many irons do you have? 2 and 3 oxygens. Like I said, nothing is created or destroyed, so if you have 1 here, you can't suddenly have 2. So we must add in coefficients to balance this chemical equation. And to do this, it's almost a trial and error kind of deal. So I would just tackle one atom at a time and see what you get. And if it doesn't work, start over. So for example, I'm just going to blindly say, okay, I'm going to start with iron. If there's 1 here and 2 here, how do I make that balance? 1 can multiply what number to become 2, right? 2. So I say to myself, if I put a coefficient of 2 on iron, 2 times that, this makes that a 2. Then I go to the next guy, oxygen. So 2 and 3. So you probably have to find a lowest common factor between them. So the easiest one I think about here is, what's 2 times 3? 6, right? So if I had 6 oxygens in the beginning and at the end, it will be the same. So I ask myself, what needs to multiply itself to become 6? Right? 2 times 3. Right? So 3 times 2 is 6. On the opposite side, I also need to make this become a 6. So 3 times what equals 6? 3 times 2, right? 2 times 3 is now 6. Now be careful. Do it like this all the time, where you add in the subscript and then multiply it out so you see the consequence. But don't forget the other guy. 2 times 2 is now 4, right? Whenever you change coefficient, it changes the whole molecule. Now, you see how this is trial and error? We had iron good, and then when we tried to fix oxygen, it messed up our iron count. That's okay. We can just go back. Now let's go back to the iron. Again, this was 4. This is now 4, and this is 2. Well, how can I make this side to become 4? The coefficient cannot be 2 anymore. It has to be 4, right? So 4 times iron is 4 irons. So let's double check at the end. 4, 4, 6, 6, and we're good. The last thing you want to check is to see if these coefficients can be are the minimum ratio possible. And it seems like they are, 4 to 3 to 2. There's nothing you can divide that is common in all of those numbers. What I mean by that is, for example, if this, and this is fake, right? If this was 4 to 2 to 2, can you have, the ratio is 4 to 2 to 2. Can we reduce that ratio? Is there a number we can divide for all of those numbers? Yes, right? You can divide all those numbers by 2. If you divide all these numbers by 2, you would get that this is 2, 1, and 1. Okay, so if that were to happen, you would want to do that. Again, that doesn't apply for this one because this was a 3 and not a 2. Okay, so now let's take a look at a different case where it might be a little bit trickier, but I'll show you a trick that will help you solve these kind of problems. And the type of problems is balancing equations with polyatomic ions in them. And the trick with them is to balance them as an entity, balance them together. So I'll give you an example to see what I mean. Okay, so this is your unbalanced equation. Some of you might be tempted to do the accounting of the atoms by listing all of the atoms out. Right? Those are all the atoms in this molecule. Someone suggests you not do that, and my suggestion is to put all the polyatomics together. You see how PO4 exists on this side, and it also exists as an entity on this side. Right? So you can basically balance them as if they are one thing. Just write PO4 like that. Okay, so now let's do the accounting. Sodium is, on this side, 3. Phosphate, that group, there's only 1 phosphate. Magnesium, there's 1. Chloride, there's 2. On this side, magnesium, there's 3. Phosphate, there's 2. Sodium, there's 1. And chloride, there's 1. Okay, so let's start balancing this guy. We've got sodium, 3 and 1. So maybe put a 3 here, because that would make that a 3. But also what? Chloride is now a 3. Let's now go to the phosphate. This was a 2 here, and this is a 1 here, so I need to do what? I need to make this a 2, right? And how am I going to make this a 2? I need to multiply this by 2. Right, because 2 times 1 phosphate is 2 phosphates. And notice what else happens. This changes sodium too, right? 2 times 3, that's now 6. So we might want to go back and change this one because now sodium has changed. Instead of multiplying by 3, instead we need to multiply by what? We have 6 sodium, right? So we have to have it multiplied by 6. That means this 3 is now 6. Yay, balance. Remember the chlorides also changed? Okay, so let's go down the list again. Sodium is good, phosphate is good. Magnesium, there's 3 there and 1 here, so we need to multiply this by 3. 3 times magnesium, 1 magnesium is 3. 3 times chloride, there's 2 of that, so that makes this a 6. That makes everything balanced. 6, 6, 2, 2, 3, 3, 6, 6. Okay, so just have a lot of practice on this. It's actually fun, huh? Alright, so let's balance this equation. Again, I'm going to write all my elements out. We don't have a polyatomics in this case, so I don't need to write polyatomics. Aluminum, in this case, there's 1, hydrogen 1, chloride 1. Aluminum, on the right hand side, there's 1, chloride, there's 3, hydrogen, there's 2. Okay? Now, remember that we can only add in coefficients when you balance chemical equations. You can't change the subscript. Again, you have to have the right subscript in order to balance the chemical equation. So that's two components, right? If you can't write the chemical compound correctly, then you can't really balance the equation, because that's the thing you cannot change anymore. Right, so we have aluminum, nothing to change there. Hydrogen, there's 2 there and 1 here, so I'm going to say 2. That makes this a 2 and this a 2. Oh no, chloride, 2 and 3. There's no number that they can be together, so you think about the lowest common factor. That's 6, right? So how do I make this become 6? Instead of 2, you put a 6 here. And now this hydrogen becomes 6 too then. Okay. Again, let's stick with the chloride. If this is 6, how do I make this to become a 6? That means I have to make this a 2, right? 2 times 3 is 6. Remember, whenever you write the coefficient, apply it immediately, or else you might forget later on. So I'm going to apply it right now. 2 times 1 is 2 for the aluminum. Doesn't seem like it's working out so far, so I can keep on going though. So I changed aluminum, so now I'm going to put 2 aluminum here. Hey, yay, at least that doesn't change much. How about hydrogen? That's not balanced yet. There's 6 here and 2 here. What must I put here? 1 times 2 becomes 6. 3 times 2 is 6. 6 and 6. Yay! So my ratio is 2 to 6 to 2 to 3. Do I need to reduce it any further? There's no number that can reduce it any further, right? So that's those are my coefficients. So the answer is D. 6 is the coefficient for HCl.